I²CNER seminar series. The I²CNER seminar series was launched in 2010 upon the inception of the I²CNER seminar series has featured the best researchers in the world on carbon neutral energy issues. I'm Shoji Kyushu University, and I will host today. Today we welcome Professor Matteo Bucchi, and let me first give a brief biography of Matteo Bucchi. Professor Matteo Bucchi is Associate Professor of Nuclear Science and Engineering at the MIT. He received his PhD from University of Pisa, Italy in 2009. He joined the French Atomic Energy Commission in France as a research scientist in 2009. He moved to MIT as a research scientist in 2015, and he became an associate professor in 2021. He has published over 40 journal articles and 70 conference papers. His research group studies two-phase heat transfer mechanisms in nuclear reactors and space systems, develops high-resolution, non-intrusive device and surface engineering techniques to enhance two-phase heat transfer. He has won a lot of awards for his research and teaching. Matteo serves as the editor of Applied Thermal Engineering. He is a world-renowned researcher in the field of boiling. Now, everyone, please welcome Professor Bucchi, and please start.
Thank you. First of all, thank you very much for your kind introduction, Professor Soji, and thank you all for having me here. It's a great honor for me. After 3 trials, to be here with you and spend such a cheerful time in Fukuoka and meet friends that I haven't seen in a while, I have to say, so since pre-pandemic. I used to start my presentation with a video. This is a video that I'm particularly attached to. It's our first visualization of boiling in nuclear reactor conditions. Okay, so if you are in nuclear engineering, you know that light water reactor, and particularly boiling water reactor, operate at high pressure, typically in the order of 70, 75 bars. And it's and this video here actually was taken in those pressure condition, in a flow condition that mimic exactly what is supposed to happen inside a nuclear reactor. So we have a slightly subcooled fluid. We have flow that goes from the bottom to the top, and most importantly, we have boiling on the surface of this, nuclear reactor cladding. Let me call it like that. Now, one thing that you may notice, perhaps not at the bottom of the room, but those in the first line, is the length scale, the scale bar that you have there. That's 100 microns, and for those that need to relate this quantity, that's basically as thick as a hair. Okay, so what you have here is, practically speaking, a width that is approximately 10 hair, and this is important to give you an idea of how tiny bubbles can be in nuclear reactor conditions. Another aspect that is very important is time. This video was taken at 40,000 images per second. Okay, so not only these bubbles are very small, but they actually live a very short time. So to be able to image this process, we need to have a high temporal and spatial resolution. And if I may say, more importantly, we need to design an experiment that allows us to visualize this phenomenon. Okay. All right, with this parenthesis, let me start the presentation. Now, the example I show you obviously pertains to nuclear systems. Boiling heat transfer is ubiquitous. We can find it in many applications, and I'm particularly interested in space propulsion and energy storage research these days, particularly for cryogenic applications. or on the left side, electronic cooling application. So we can use bonding heat transfer to remove a very large heat flux from computer chips, and that is important to unlock the development of more and more powerful computers, and also, and importantly, to go back to the I²CNER to reduce carbon emission from data center, which is an elephant in the room in terms of carbon emissions. Okay. Now, before the seminar, I went back and looked at the first paper by Nukiyama, 1934. Okay, so basically almost 100 years ago. And we're still studying bonding heat transfer. And my colleagues often ask me, what do you have to learn that you haven't learned in 100 years? Well, the answer is a lot. Okay, and the idea is that bonding heat transfer is highly dependent on the operating condition and the surface condition and the topology of the flow and so on. So there's a lot to understand, which is application specific. We can't design space rockets with the same tools that we use to design electronic cooling devices. Okay. Second point is that even where it's known or relatively known, such as a nuclear system, we want to maximize performance. 50 years ago, it was okay to operate reactors with large margins of conservatism. That may not be acceptable anymore from an economic standpoint. So we need to improve our capability of designing and through understanding the process these reactors. And particularly, since I was talking about nuclear system, again, the elephant in the room is the boiling crisis. Okay, boiling crisis is what Nukiyama first published in 1934, and it's essentially the failure of the boiling process. This is a video that a colleague of mine years ago took with his phone. At that time, we didn't even have a powerful iPhone. That was taken probably with a simple phone. And essentially, this video represents the simplest possible experiment that we can do in bonding heat transfer. You take a nickel wire, you circulate current by Joule effect. That wire will release heat. And if you increase the current, you increase the heat flux, you will have more and more bubbles. But while this process is very effective, there is an end to it. If you have too many bubbles, which means basically if the heat flux is too high, the wire will be covered by a vapor layer, and that's basically a very poor heat transfer mode. If that happens, the temperature of your wire will grow instantaneously up to perhaps a melting point, and the wire will burn. Okay, so at that point at which this phenomenon, this boiling crisis occurs, is known as CHF, or properly speaking, Nukiyama point. And it's a big deal in my research. Now, in my laboratory, essentially, we study, as I said, nuclear reactor thermal hydraulics, but also boiling related to space propulsion application, electronic cooling, and advanced operation and learning methods. These applications are typically informed by a fundamental study that we conduct on, for instance, single bubbles. This is an exercise which is very useful for people that want to develop high fidelity simulation tools, or at more, global scale. Oh, let me go back, sorry. On a collective effect. Don't look at one bubble, but focus more on the way that bubbles interact with each other. And the reason for that is that we believe that this process of interaction is actually very, very important. So somehow we can't learn all we have to learn from boiling just looking at an individual bubble, as much as we like individual bubbles. Okay, so in the first part of the talk, I will discuss very quickly diagnostics. So the tools that over the years we have developed and used to shed light on this phenomenon. And the first one that comes to my mind is the infrared thermometry. Now I go back to this video here because in this video you can see that at some point there are some kind of flames. Obviously these are not flames. That's just a light emitted by the surface as it gets hotter. Okay. Now every kind of body will emit a radiation proportional to its temperature. Okay. So the idea is to use this radiation to measure temperature and heat fluxes on boiling surfaces. So for for our specific case of infrared investigations, it's the best wavelength that we can use is a 3 to 5 microns range, which is basically an infrared radiation. And so the idea is to take that wire and actually coat it on the surface of a substrate which is infrared transparent. So what you see here, what you call the interface, essentially will play the role of the wire that I described before. And since this interface is infrared opaque, I can record the radiation emitted by that interface with an IR camera, and practically speaking, measure time-dependent temperature and heat flux distribution. This is a kind of diagnostic that was pioneered by Teofano Zendini in Santa Barbara in the early 2000s. We have spent a big deal of time to improve the quantitative aspect of this technique without going into the detail. The real problem for this technique is to get to a point where we can really trust the measurements. And particularly, this is a problem because we have to account for the presence of participating media. So calibration of these kind of measurements, as some of you may know, and particularly Bucchi Sensei knows, is a big deal. Okay, without going into the detail, just keep in mind that to get to these nice videos, you have essentially to solve an inverse problem coupling thermal conduction in the solids and optical radiation in the space. Now, infrared thermometry is very powerful, okay, but it has limitations. One limitation is that it essentially works with wavelengths that are in the order of 3 to 5 microns. Okay, so there is a limit to the size of the object, to the size of the feature that you can actually detect. Okay, so when you look at those high pressure bubbles, basically you have more than a bubble per pixel. So it doesn't really help you. And the other limitation is due to the existing infrared cameras. Detectors for infrared are not as powerful as high-speed video detectors. So essentially, in the market, at least for now, you don't have instruments that give you the required spatial and time resolution. So for certain type of applications, it is essentially necessary to resort to high-speed video techniques. And here you have an example of a technique called color LED base phase detection, which is essentially a form of a total infernal detection technique. And the idea is very simple. We can use the same exact either as before, okay, assuming that this surface in green here is visible light transparent. And by looking at how light is reflected by the surface, essentially track the presence of bubbles on the surface itself. So what you have here on the top is an example of a measurement conducted with a red LED light, which allow you to identify dry spots on the surface, which are in bright, liquid covered area, which is in black, and also if you have micro layers on the surface, you will see these kind of interference ranges. You can play with color, so going from red to blue will reduce the resolution. But for instance, it will allow you not only to look at the dry spots and the micro layer, but also to look at the optical footprint of the bubble, which is essentially the bubble size in the optical path. And the micro layer that you see here will likely form if you boil water at ambient temperature. If you are in nuclear reactor condition, it's an example of what you will see. Now, I understand that the resolution may not be enough for everybody to look at the details, but the bottom line is that for high pressure water, such as for dielectric fluids or liquid nitrogen, so essentially fluids with a low latent heat, this microlayer will most likely not form, even though they are very, very wetting. Now, I want to give you an example of how we can use these techniques. Well, this is a schematic of our high pressure phloboning apparatus, which is the one where we have obtained the video I showed you in the beginning. And the idea is that we can combine simultaneously all this technique to get a fairly comprehensive picture of this phenomena. Okay, and I will give you in a minute some example. Now, going to the fundamentals, right? So I said we're generally speaking interested on any kind of separate effect study. Particularly, we've done a lot of work in the past and also in the present on determining condition for bubble nucleation and studying bubble growth, and also, and importantly, how surface affects this process. Because as we know, nucleation temperature are highly dependent on the surface wettability and morphology. Now, what you have here, unfortunately, is not synchronized, but the idea is that we can reconstruct the temperature distribution and the efflux distribution on the surface, as well as the temperature distribution underneath the bubble as the microlayer evaporates. And you can see this because the surface here, just 1 second, gets cold, and that's because microlayer essentially evaporation is draining out of the substrate energy. And we use this not just for the sake of science, but also, and importantly, to inform the work of people that develop scientific tools of direct numerical simulation of boiling processes. Okay. Now, in this technique, we can only measure the temperature and efflux distribution on the surface. In the past, we have made efforts to measure the temperature also in the liquid. So basically, in the region of liquid that surrounds the bubble. This was done in collaboration with Professor Marquides from Imperial College. Essentially, what we do is we use a two-dye laser-induced fluorescence technique, where we have one dye that serves to trace the intensity of light, and the other one, which is a temperature sensitive, that essentially allows us to measure the temperature. And this is still in pool bonding. And here what you have is an example of flow bonding experiments, where we look at exactly individual bubbles, how they transfer energy, and the fact that, for instance, in flow bonding, due to the presence of the flow, the growth of the bubble is not axisymmetric. There is a certain level of torsion in the bubble, and that way affect the rate of heat transfer in the microlayer, and consequently the total heat flux partitioning in the process. Now, what I show you here is, again, is for individual bubbles. And now I want to move a little bit towards the applications and also the fundamental study that we do towards these applications. Now, one important number that we should remember in, well, I don't know why it doesn't work. Okay, in boiling heat transfer in nuclear reactor is 7,000. Okay, 7,000 is the surface of heat transfer in a nuclear reactor core. 7,000 square meter is, for those of you that like soccer, basically the size of a soccer field. Okay, and so the idea, guys, is that even though we can have a lot of fun developing those beautiful DNS models, we are not even close to be able to use DNS to study boiling heat transfer in nuclear reactors. Okay, so the state-of-the-art approach, essentially for this kind of application, is still very much relying on modeling. Okay, so even CFD models, for instance, to date rely on the subgrid model to calculate the heat transfer coefficient and the vapor generation rate on the wall. Okay, and what you have here is an example of probably the most popular model, which is known as RPI model by Krul and Podolsky. And the idea is very simple, basically. Take every single bubble, model how this bubble is transfer energy with the surface or from the surface, and reconstruct the total heat flux as the sum of different contributions related to the growth, so the evaporation of the bubble, the quenching, which is what happens when bubble leave the surface, or anywhere else where you don't have boiling, essentially some kind of convective effect. Now, this is the approach, and this model dates 1990. In 2013, DOE in the United States started a big effort called CASL, Consortium for Advanced Simulation of Light Water Reactors, that had among the different milestones want to reassess this model and come up with a more comprehensive way to essentially model this phenomena. And a colleague of mine in particular was in charge of this effort, Emilio Baietto, and they came up with a fairly, comprehensive framework, and looking at how possibly all, these phenomena would essentially interact with each other, but leaving with a very, a big question mark. How do we validate such kind of model? Okay, how can we say demonstrate that the prediction that you can get out of this model are not the results of an overfitting or a tuning of the countless variables and parameters that you have inside? So that's where essentially we went back to work and essentially take back those nice temperature and flux distribution and started to measure boiling quantities. Okay, so the idea was let's try to understand what we can learn quantitatively about the boiling process. And now, basically, by looking at this distribution, we can identify points on the surface where bubble pops out. Those are nucleation sites. Okay, and we can count how many nucleation sites we have as a function of the operating conditions. But importantly, we can track the history of temperature and flux at each nucleation site and understand how many bubbles we have per second. Okay, how much it takes for a bubble to grow, how much do you have to wait before the next bubble come out of the same nucleation site. So essentially, we had a large amount of data to process and to be able to quantify the time scale and length scale that define the boiling process, which essentially are nucleation site density, bubble growth time, wait time, frequency, and also importantly bubble size, bubble footprint. And so we were able to inform their development, but also importantly, one parameter that we succeeded measuring is the total amount of energy removed by evaporation of a microlayer instead of quenching or instead of other heat transfer mechanism. And this was important because at that point, with the modeling framework, people started to not just look at the boiling curve as a term of comparison, but to actually try to reproduce each one of these individual mechanisms in detail. Okay. And well, the bottom line, and we're still addressing this point, to be honest, is that even in boiling heat transfer, most of the energy is still removed by convective flows. Okay, even in turbulent forced convection, when bubbles come out of the surface, you have a very, very large increase of the heat transfer in the non-boiling areas, and that heat transfer essentially cannot be explained by simple, reduction of the hydraulic diameter or other phenomena. There are important questions that still, are open to be able to predict how much and how come that heat transfer coefficient in the region where you don't have boiling on the surface, essentially as soon as you start to boil, increase up to a factor 8 or 9. Okay, so this is an important open question that these days we're still trying to address. Now, in the past, all these investigations essentially rely on heaters that are made of sapphire substrate, so infrared transparent glasses, and typically are coated with indium tin oxide. Okay. Now there are two major issues with these heaters. First one is that indium tin oxide is non-smooth. Nuclear reactor claddings are not. Okay. And the second one is that sapphire has perhaps different thermophysical properties compared to the materials of interest. Now, the first issue is real. The second issue is not. Sapphire is as close as zircaloy and stainless steel as it gets. Okay, copper is much different, but sapphire, stainless steel, and zircaloy are very similar. The real problem remains the surface. Okay, so in the past, we started to think about ways to not just do infrared thermometry, but do infrared thermometry on surfaces that are representative of nuclear reactor conditions. And so we come up with ideas to engineer that surface. And obviously you can put coatings, but the major advances was when we were able to make first time heaters that essentially have the same roughness And so essentially the same surface finish and wettability as materials of commercial interest. And something which we did very recently is actually to engineer pillars on top of that surface. Okay, and this was a big scientific endeavor from my point of view, because so far people have not been able to actually measure the heat flux and temperature distribution at the pillar base. And these pillars are very popular in electronic cooling. People want to use them by etching silicon. But from a scientific point of view, it's still not clear why this enhancement is possible and how it happens. So actually, I want to give you here an example of what we did on these pillars, and try to raise your interest to learn more. By the way, this is all published work. You can find it in literature. I can send you paper if you're interested. Now, what you have here is a comparison between a plane surface, such as ITO, and a surface where we have pillars. And if you can't follow me here, you see that on the plane surface, when the bubble nucleate, they grow and the microlayer evaporates. And essentially, when the microlayer is evaporated, the heat flux gets to zero because the surface is dry. Okay, but if you look at the bottom surface, okay, you'll see that the growth of bubble never results in a dry out of the surface. So bubbles keep growing and the surface never gets dry. You always have a very high consistent level of heat flux. Okay, so essentially the dry, say the bubble patch on a surface with micropillars behave in a much dramatic, much different way compared to a plane surface. Now, something we did is to plot the distribution, process this distribution in time and space to get a sense of not just the average heat flux and temperature on the surface, but also how this temperature heat flux are distributed. So for instance, this is a bivariate distribution of temperature and heat flux on a plane surface, and you recognize here that there's a central value. That would be just the average surface and temperature and heat flux. When you do the same processing on this kind of results, you realize that you have two peaks. Okay, the first peak here is basically nucleate boiling, conventionally said. This peak here is the evaporation of the bubble-based liquid. And this is for the same average heat flux condition. I forgot to put the value here. But the idea is that you can do this for all operating conditions, all the way to boiling crisis. And basically, that's what you would obtain. In a plane surface, basically, this distribution overlap with the average value of the temperature and heat flux. But on the surface with pillars, you see that there is a consistent separation between what we call a nucleate bonding signature and this part here, which is a so-called evaporation of the intrapillar liquid layer region. And the major finding was that no matter the presence of this mechanism, actually that evaporation removes very little energy. So underneath the bubble, the evaporation of that liquid doesn't take off the surface more than 30% of the energy, which was a fairly surprising finding, because many of the theories that aim at characterizing these pillars actually rely on the evaporation of this liquid layer wicked or trapped as the reason for the enhancement. Anyway, long story short, this was our study. Now, one of the perhaps most important contribution in the last couple of years from our group is the one on the scale-free nature of the boiling crisis. A few of you may have seen this a couple of times already, and I apologize for repeating over and over again myself. Now, what does it mean, the scale-free nature of the boiling crisis? Well, first of all, let me explain to you what you see here. Now, we have different kind of experiments. Okay, it can be probe bonding, it can be flow bonding, it can be with water, it can be called liquid nitrogen, it can be with dielectric. Okay, and obviously, when you plot the boiling curves or Nukiyama curves, they will all have a different kind of shape. Okay, so different critical heat flux and different heat transfer coefficient. But the finding that surprised us was that no matter the boiling curve or the heat transfer coefficient or the CHF, in the moment where we have the boiling crisis, the distribution of this bubble footprint area will always be essentially a power law, a straight line in this log-log plot, okay? And these power law in particular are called a scale-free distribution. The exponent is smaller than 3. And the reason is that basically the exponent is smaller than 3, the standard deviation of that distribution becomes infinite, okay? So basically you cannot define the behavior of this system using a central value like you will do in a normal distribution. And by the way, for Christmas I got a gift, and when I went through the book, I found that many years ago, actually, in 1998, using a technique similar to ours, Professor Nishio and Nagai found very similar results using refrigerants. So essentially, this CHF condition, which I cover with the orange line, happens to be a distribution very, very similar to the one that we observed on water and other kind of fluids later on. Now, going back to the distribution, and very quickly, for interest of time, the idea was that this distribution results from an interaction process of the bubbles. When you have little bubbles, basically bubbles live separate. They don't, say, interact much. Every bubble is independent. But the scale-free distribution emerge as the results of a bubble interaction process, okay? Now, the idea is that the more bubble you have, the more interaction you will have on the bubbles. And to capture this process of interaction, we look at experimental measured bubble growth time and frequency, so basically the probability of having bubbles on the surface. The bubble nucleation site density, so essentially how many bubbles we have on the surface, and the bubble size, okay? And we try to duplicate this experimental distribution using a simple Monte Carlo model, very, very simple model. Basically look at, basically generate bubbles randomly on the surface, accounting for interaction, for deactivation, and then tracking the areas of these big patches, essentially duplicate exactly the behavior that we had observed experimentally, okay? And this was very, very interesting for us. The other part was that essentially we wanted to convert this mechanism into some kind of a more useful tool. And so what we observe is that this kind of instability in the process, this power law distribution, coincide with a situation where the largest patch here, which called a giant cluster, and the second possible giant cluster of bubbles, essentially diverge. If you are in a nuclear boiling, these two quantities will have more or less the same size, okay? But in the moment where you have this boiling crisis with this power law distribution, what will happen is that you have a bifurcation in this process. So basically, we are in front of a first order instability in the system. There is only so many bubbles that the system can accommodate before they collapse altogether, they coalesce altogether, okay? And we were able not just to, find this mechanism, but to translate this mechanism into a non-dimensional law, which is very simple. N double prime pi r square FTG equal to 1. So these are our boiling parameters. If the operating conditions are such that this number is less than 1, we are at the left of this curve, and that's basically nuclear boiling. But in the moment where this parameter hit 1, which occurs for the highest heat flux for each curve, you have a boiling crisis. And what you have here is an example of, I think, 11 different surfaces and operating conditions. This includes flow boiling, pool boiling, also liquid nitrogen, if I'm not mistaken. I think liquid nitrogen should be somewhere here. But anyway, I'm quite sure. Okay. So And why we use this? Well, this essentially will give us the closure relationship to estimate critical efflux starting from efflux partitioning model. So that's where we're working now. Actually, we have an example of this already published on the rough surface that I mentioned before. Now, switching a bit gear and essentially, if you allow me also in a more superficial way, relevant to nuclear reactor and particularly experimental nuclear reactor, we did in the past a lot of work on effect of the transient heating on the surface. So there are important effects that should be accounted for in the design of an experimental reactor, in particular in case of a reactivity-initiated accident. So we studied the effect of a power escalation period during an exponential power rise for different kinds of surfaces. I'm going quick here. If you have any question, I can get back to this later. For the people that study nuclear material, we conducted work on characterization of accident-tolerant fuel materials, trying to explain the difference between conventional zircaloy and claddings coated with chromium coatings or silicon carbide and so on. The bottom line is practically there's no difference. Okay, so the Nuclear Regulatory Commission was very happy with that. This is an example of a study of oxidation where we took a zircaloy, we boiled on zircaloy, we oxidized the same sample, we boil on the same sample, we reoxidize and we reboil on the same sample. Basically to show that there's no difference due to the effect of wettability due to the oxidation of the surface, how the oxidation really change in morphology. And this was important because if you look at much of the literature that you find in nuclear journals, there is a big, essentially, let me allow the use of the word confusion, for lack of a better word, on what the real effect of wettability are. My understanding is that there's absolutely no effect unless the oxidation transition to a post-transition oxide where the surface becomes porous, and at that point, it's not the wettability, it's really the surface morphology that changes and the boiling process as well. Okay, now high pressure probe bonding. This is an example of the fidelity study we conducted in bonding heat transfer. So going back to the initial video, we started to look and analyze exactly the dynamic of bubbles in high pressure conditions. So we're using the same diagnostic here to track the growth and sliding of bubbles with time. The idea is here to try to understand this mechanism of growth and nucleation and growth and the sliding and departure of bubbles in nuclear reactor conditions. So we have here this test that we try to capture this phenomena using first principles. So essentially force balance approaches to track the bubble sliding. And also, and importantly, be able to predict how this phenomena of growth and departure scale with pressure depending on the operating condition. And this is an example here of a paper that is currently under review. Now, we shouldn't allow me this comment, and don't want to be pretentious. Allow me to emphasize this. These are not easy experiments to run. It took us almost 5 years to put this experiment up and running, let alone understand the data. That's a much bigger endeavor. And well, here you have obviously nucleation site density as a function of different operating conditions. So this is simply speaking a processing of the videos. And then, yeah, here I want to open a different parenthesis because obviously all the things that I have explained so far relates mostly to departure from nuclear bonding condition, which is what happens in PWR. But for bonding water reactor, the failure mode is dry out. Okay, dry out occurs when the liquid film in contact with nuclear fuel cladding essentially disappears. Okay, the question is why it disappears. Okay, and if you look at many of the correlation, basically assume that this dry out occurs because of a de-entrainment, because of evaporation, depending on operating conditions. Now, with the push of DOE, we started to look at how this happens. Okay, And so we developed another apparatus to study the same boiling process, but on a much longer surface. And infrared thermometry much longer means 10 centimeters, basically. You can't do much more than that because of the aspect ratio of the sensor. But what we did is we developed an apparatus where we can prepare the flow condition upstream. Okay, so reach essentially a flow which is in thermodynamic equilibrium, and then let it flow through this test section where we actively supply energy as always, okay, to this ITO surface. And then look at the different, essentially boiling curves and different flow regimes, spanning going from subcooled nuclear boiling to a saturated bubbly flow, okay, which is this one, when you have a little bit of a slug flow here, slug plug, churn flow, and last but not least, obviously, you have annular flow, okay? This was done at low pressure for the sake of clarity. And when you look at the boiling curve in the CHF, the amazing results that we found is that, oops, I think I crashed. It happens all the time. Okay, let me be sure to skip this slide that crashed. So, okay, so here is what we observe. So essentially, in subcooled flow, as you decrease subcooling, you have decrease in CHF. That's quite normal. Most important and interesting part is what happens here. Okay. Now, what you see is that there is kind of a maximum in the annular flow regime. Okay. And so, for instance, for 6.9% of voids, we are here. 8.6, we're here. For 22 and 26, we are here. Now, if you look at these videos, is infrared video. Different images. And the difference is that in this case, liquid is boiling within the film. Okay. In this case, the liquid is so thin that basically nucleation is suppressed. And so our prediction now is that basically, if the liquid film is thick, the process that dry out actually some kind of departure from nuclear boiling in liquid film. If the liquid film is thin enough to suppress nucleation, then you have, let me say, conventional dry out process. That's with okay. Okay, I can't believe it happened. All right, so I want to maybe spend minutes, if you don't mind, just other fluids. This is our research for space propulsion applications, where we look at boiling and quenching of cryogenic fluids. This is relevant to propulsion because fuel is typically stored in the form of liquefied gas. We're talking about oxygen, hydrogen, methane. We simulate, for now, these fluids with liquid nitrogen, okay, for safety reasons. But the idea is that while we can do, obviously, infrared thermometry, we can still deploy phase detection and shadowgraphy to understand the dynamic of bubbles on the surface and essentially, again, teach the people that develop computer tools how to simulate these processes. I mean, if my colleagues heard me, I said teach, it will be mad with me, will say help, okay? And so, for instance, example of a study that we have done is to evaluate the effect of gravity in bonding of full bonding of liquid nitrogen. Essentially, here you have, simply speaking, the value of the critical flux versus the orientation angle. So 0 is horizontally upward, 90 is vertical, and 180 is basically upside down. So as you may imagine, the CHF basically precipitates as you go from the 90-degree to the upside down surface. But again, something which is fascinating is that even for all these tests, we found the same power law distribution. So without spending too much time, I mean, we have more to process and understand here. Now, we did this in the lab, but we also have done an experiment in 0G. If you haven't done this in your life, do it. It's very fun. The first time is not so much, but as you get used to microgravity, it's get very, very fascinating. It's a very nice experience. So we did this for, again, to simulate microgravity, not just minus 1G. We did also a microgravity test with Professor Di Marco, University of Pisa. In this case, they use, this is not propulsion, it's electronic cooling of satellites. So we're now dealing here with electronic cooling. We don't use water, we don't use cryogenic, we use dielectric fluids. What we have here is test with an FC72. And the idea was to essentially use a microstructure surface combined with electric fields to reestablish in microgravity conditions the shaft that you normally will have in ambient on Earth. And the idea is that if you do this experiment in microgravity, normally you will measure very, very low influxes, critical influx. Okay, now let me skip this one. For the sake of time, just one words about machine learning. Obviously, we generate a lot of data. It is really difficult to manage at this point. And the day where everything works fine, we can generate up to 2 terabytes of data. Okay. Now you have to store that, but especially you have to process those data. Versus Bucchi is laughing because he knows any of this data will never be processed. Okay. So in the past, we started to think about ways to use machine learning to do this work for us. Okay, and well, I can say I'm not a machine learning expert, but it works. Okay, so the bottom line is that using simple convolutional neural networks, we can almost say do real-time processing of this video. So essentially, the quantity as we run experiments. Okay, all right. So with this, I think I will stop here for the interest of time. I just want to spend 1 second to thank all the collaborators of the world and my students. Obviously, particular acknowledgement goes to Professor Mori, Professor Takata, and the Japanese Society for the Promotion of Science that allowed me to be here. And if you have interest in discussing about bond transport research, please join us every 2 or 3 weeks online with a group of scientists around the world that discuss research and particularly promotes the work of junior faculty. I think we had Kita Sensei and Wang Sensei a few months ago. I hope you have a new assistant professor to come and present research. And I think you have Kita Sensei here, and if I'm not mistaken, that's Takata Sensei as well. Okay, and I believe that Suzuki is actually from Oku University. So even in Japan is often late at night, you have many people showing up, and that's definitely a very, very inspiring and rewarding. Okay, if you can't attend the seminar, just go on the YouTube channel and watch the video. All right, with this, I will finish. And thank you very much for your patience, especially for the ECAP. And I'll be glad to answer your questions.
And is there any question from the audience? Please.
So thank you very much, Matteo. Very extensive work. And I have some one question about the you show the many data about the critical heat flux, right?
Mm-hmm.
So did you compare with some existing correlations with the, for instance, for the flow voiding cases, maybe there is I'm not familiar with the, for instance, Professor Kato's correlation.
Yeah, they are in the ballpark. They're in the ballpark of what you will predict with Kato Amore, if I'm not mistaken, and other correlations. They more or less end up in that range. For the annual flow boiling test, that's actually a little bit trickier because most of the data for that range are obtained using very long geometries. Okay, so there the comparison is not really helpful to it. CHF data for those kind of phenomena are typically integral data. You look more at the total energy to the fluid. the aim of what we try to do is to provide a local criterion for annular flow boiling crisis. Okay, to answer your question is they very much they are in the plus 20–30% of what you would predict with correlation, which I think is typical of any data at this stage.
If my memory is correct, you mentioned that the effect of the surface wettability is not so much compared with
The
roughness.
Yeah.
Mm.
So this actually is very surprising. If you look at the literature, it's kind of counterintuitive. But let me tell you how we came to that conclusion. Okay, so this relates especially to the effect of oxidation on zircaloy. Now, there are many people that do very rigorous work, right? They take samples of zircaloy, they take one, they do the boiling test, then they take another one, they oxidize, and they measure another level of CHF, right?
Mm-hmm.
And say, okay, this surface has a higher wettability than higher CHF. Now, the student that did this, Sun Ji-young, she prepared 16 samples, all identical, okay? She boiled all the 16 samples, fresh samples. And basically, we observed a scatter in the data, which was, even though the surface was nominally identical, way larger than the difference we had between a fresh and an oxidized surface. So what we decided to do is to say, let's take the same surface, boil, oxidize the same surface, reboil, oxidize, reboil. And not only that, but also at every step, we did SEM, AFM quantification of the surface parameters, contact angle, and so on. And so we noticed that essentially zircaloy evolves through different phases. But during the first phases, the morphology remains the same, although the wettability changed. And the outcome on boiling process was basically no difference.
So is it because of flow boiling?
It may be. So it's actually something which we did in flow boiling. We should do it in pool boiling as well. So in our conclusion, actually, remember distinctly we wrote is maybe related to the fact that the bubble dynamic is driven by the flow. But maybe it's good to do pool boiling as well, because I can't answer that question, but I think it's a very, very good idea.
Thank you very much.
Thank you.
So, Shen-san, please unmute and please.
All right. Can you hear my voice?
Yeah, Shen?
Yes.
Yes. This is Shen from I² University. Sorry, Matteo, I couldn't be there in Fukuoka because I don't have any budget left. I'm very, very impressed by your presentation. Like, particularly, I find the model about the boiling crisis, the CHO model, very, very interesting. Can you just go to that slide and show the result again? I think it's maybe slide 34, 35.
This one?
Yes, this one. Yeah, like yeah, I see this model can explain like how CHF happened very well, but I cannot help noticing that all the parameters are measured parameters, right? So there is no way to know like what the value for M and like frequency and also TG, right? Do you have any idea like about like how to move one step further to give like predictive power to this model?
Well, thank you very much, Biao. So in fact, if you think about this, that's what you have to do no matter what for heat flux partitioning.
Right.
Right. So in heat flux partitioning, you have to be able to provide the scaling for these parameters no matter what.
Yeah.
Right?
Yeah.
So
yeah.
the big question here is, I wish I had another slide. I have another slide on the deck, on another deck that would be useful. But this criterion, essentially this instability,
Right.
okay, depends on the interaction of these parameters. Now,
Yeah.
these
yeah.
parameters will still depend on the operating condition and the surface and the fluid you're
Yeah.
using. So the big question is, in fact, can we predict those parameters starting from the surface? Okay. So that step was, no matter what, we will have to take it.
Mm,
And so the idea by doing these measurements, and particularly those at high pressure condition that I started to show you, is to be able to mechanistically
right.
essentially predict each single block of this
Yeah.
non-dimensional number and use it later on.
Yeah.
Okay. But it's a, you know, I think the difficulty now is exactly that, right? Understanding how to go from
Yeah.
surface morphology to n double
Yeah.
prime or R
Yeah.
square or FTG.
Yeah. I think maybe under ideal conditions, you will have just the heat flux and the surface conditions on the left-hand side of the equation. And I guess in that way, you essentially complete boiling heat transfer research.
Well, I think it's still a long way to go.
Yeah. Yeah. Yeah.
I think there's work for everybody for many years. That's.
All right. Thank you very much.
Thank you, Bianca.
Any question and comments?
Let me confirm your experimental apparatus. And today you show the many full boiling experimental apparatus, and you visualize from this side. So my question: how did you give heat flux? Okay, so here is glass and the boiling surface. And how do you give heat? And can we decide the representative heat flux in through plane direction?
Let me use a.
Yeah.
Let me show you this one. So essentially, let me go through this very quickly. So the basis is this solid substrate, right? And then on top of that, we put IR opaque ITO. But that ITO is infrared opaque, but is also electrically conductive. Okay, so the idea is that we can connect that ITO to some kind of electric source. Okay, and so it's circulating current through this ITO that we release by Joule effect heat, which boils. And so this ITO is, as a matter of fact, less than a micron thick. Okay, so from a thermodynamic point of view, it has very little thermal capacity and thermal resistance. So from the processing point of view of the data, you can consider like a planar surface of energy, so equitable prime section. There are situations where we are able to stack up multiple layers. In that case, sometimes we have to correct for thermal capacity, especially if the layer is an insulating layer like alumina or things like that.
So this orange color.
That's gold. That's gold.
It's an insulator.
That orange layer is gold. It's gold which is used as an electrode, so we connect wire to gold, and gold is very low resistivity. So heat is only dissipated by the ITO.
But okay, so the heat wind can heat release this direction and this direction.
It goes in all directions. That's why, by the way, that's why it's very complicated to make these measurements. And so when we do this, we actually have to correct for the heat losses, okay, and for the transient effect in the substrate. So we need to solve a 3D conduction problem in the substrate, together with a radiation problem to estimate the temperature.
Okay, I see. The reason why I ask you, I am electrochemical team, and my concern is watching the bubble from electrolyzer, and I usually carefully check the total current and visualize the number of bubbles.
Yeah.
And oh, I lost the bubble or not. But okay, now I understand. So that you can possibly you can get to the total heat to the boiling
Yeah,
surface.
most of it, yes.
Okay,
And obviously we have our little secrets,
Mhm.
but yeah, most of it, yes.
okay, I see.
Is there any questions from audience? I have one question. So you showed us some ratio between the evaporation and convection.
Yeah.
So could you give us the comment about the effect of diffusion?
I can't.
You can.
I can't yet,
Uh,
but maybe I will next time we meet.
Okay.
We're doing some work in that as we speak. My feeling is that it become even more important, convection, but well, I will have to, wait to give you an answer on that.
Thank you. Any question or comment, please?
You mentioned about just use a colored LED, right?
Yeah.
Instead of laser.
No, it's not a laser. Actually,
It's not really instead of the laser.
it's the first time we did that, we did it with a mouse. So it's actually a fairly cheap light.
Okay.
You can, it's a plus minus 20 nanometers. It's actually the beauty of that technique is that by not being coherent, you reduce a lot the effect of basically parasitic reflection that normally you will have in when using lasers. Lasers will tend to amplify any kind of imperfection from the apparatus, from the surface. But using light which is not perfectly coherent, for instance, you avoid amplifying the parallelism effect between the top and bottom surface of the glass. You only measure a micron scale feature coming from the liquid. So
Okay, so
very, very cheap light.
so for this case, the LED is better.
Yeah.
Okay.
Yeah.
So what's the meaning for the color, the different color?
It depends, the coherence length changes depending on the color.
Okay.
So you can penetrate the fluid more or less. Okay, blue typically gives us a better contrast, but has a shorter coherence distance. Red has less good contrast, but has a better coherence distance. We can go up to 10 microns, and that allows us to measure the micro layer, for instance. The blue doesn't allow you to do that.
Last question. Sorry. So you mentioned about the RPI model. So the RPI model is for the pool volume for the forced convection.
It started with forced convection.
For the forced
People
convection.
have been using it for everything.
Does it include the effect of the mass flux?
It does in the parameters. We go back to the problem raised by Professor Biao-Shen, right? We need to be able to predict those parameters. Sorry, it's taking a little bit of time. Yeah, so you see these green parameters, which we call fundamental quantities, are nucleation site density, frequency, growth time,
So that's
and wait time. You have to know.
No information of the mass flux, right?
Well, the mass flux will affect the frequency of departure of bubbles, will affect the departure diameter of bubbles. So you need some models to branch in to predict how the mass flux affect those bubble parameters.
Okay, so in your pool boiling condition, you mentioned that it's a convective, is also convective heat transfer is also very important.
Yeah,
Okay.
even in
So-
pool boiling, but in particular case they show you is flow boiling.
Yeah, but so if it's a convective heat transfer is important in the pool boiling, so I think it also should be important in the convective
Oh
boiling,
yeah,
right?
absolutely.
So how to understand, so for the forced convective conditions, so the mass flux will be very, very high,
Mhm.
much higher than the convective heat transfer in the pool boiling condition.
Sure.
So the mass flux, how just incorporate this mass flux effect?
Well, the point is that
Not only effect is this
Yeah.
boiling,
Yeah.
boiling, but
So, the bubbles generate velocity fields that are comparable or even more important than the flow itself. a bubble nucleating in pool boiling can grow up to 1 meter per second, which means basically 1 millimeter per millisecond. At those distance from the wall, this velocity is definitely comparable, if not stronger, than the velocity you have in a convective boundary layer. So the reality is that the dominating velocity scale is not the one from the flow, but is the one induced by bubble nucleation and departure. Okay, so this is what I think happens. But the math makes sense. Now to go from this qualitative observation to a model, well, the way is still long, but definitely we have a bubble-induced flow that cannot be neglected. Yeah.
So, Tokuda-san, please give the question.
Can you?
Can you hear my voice?
Yes.
I'm Daiki Tokuda. I'm a member of Matteo Corporation researcher. I wonder how about the other working fluid? So you study about the water so much. So how about the other fluid, especially critical heat boiling cap?
Yeah, I mean, if you refer to the force convection aspect or generally speaking, the boiling curve.
Yeah.
Well, what I can tell you is that even for those fluids, although we cannot measure temperature and flux distribution, even for the nitrogen, we can reverse engineer the contribution of contact line evaporation and single phase heat transfer. And our understanding as of now is that convective effects are still dominant. Contact line evaporation is definitely important, but it doesn't remove more than 20–30% of the total heat for liquid nitrogen or even for the dielectric fluids. The problem is that as of now, we can't measure the time-dependent temperature and flux distribution on the spot surface with liquid nitrogen. That's because infrared thermometry doesn't, there's not enough radiation for us to make a measurement at those temperatures.
Okay, thank you.
Thank you very much.
Yeah, please. Wonderful.
I was waiting for your question.
It is just store micropillar surface.
Yeah.
How is the relation between microlayer thickness under bubble and pillar height? And is there some optimization to enhance transfer?
Okay, well, I mean, I'll have to give you the short answer now, and then we can talk all night. Okay, so my feeling is that, let me go to that plot. Actually, give me a second. Let me go to this plot. You unlock the next level of complexity. So the micropillar is 10 microns tall. We use 10, 10, 10. So the one that literature-wise maximize the critical distance. Now, this value here is, as you can see, constant. This means that basically the heat transfer coefficient in the micropillar evaporation region basically is constant, doesn't depend on temperature or influx, right? The slope is the same. Now, we were able to duplicate this essentially by looking at the morphology of the surface, okay, which you have here. And this was basically done with a surface optimization software, like a surface evolver, and predicting the evaporation by considering in particular two heat transfer modes. The one where the energy is transferred in evaporation through the pillars to the contact line, and the evaporation occurs mostly at the contact line. And the other one where basically the evaporation occurs over the surface here, and basically goes from the base to the liquid interface. Okay, so the first mode, the one on the contact line, prevails when the liquid thickness is high, okay? And that's because the path for energy to go through the pillars is thermally shorter than to go through water. But when the liquid film thickness becomes very, very thin, then at that point, it's faster to go through the liquid, okay? Now, what is the outcome of my message? Message is that if you have to go through the pillars and evaporate on the contact line, fundamentally your heat transfer coefficient should be dependent on the contact line density and independent on the pillar height. So working hypothesis that we are testing is that basically we should have, this is slope here, this slope here, it should be proportional to the contact line density, okay? And that's an hypothesis that we're trying to test. But making those heaters, to me, is a nightmare. It's a nightmare. Did I answer your question?
Yes.
Okay.
That's interesting.
Yeah.
You mentioned about the ATF theory.
Yeah.
Okay, the research on this. So what do you think is the most important research topics for the ATF? Of course, for the heat transfer.
Yeah, people online. I think it's the most important part as of now is post-critical influx.
Critical.
Post-critical influx. I think that, there is no major difference, especially in high pressure conditions, right? So let me spend 1 second here. So this is a comparison between uncoated rod and coated rods for chromium coating and bare surfaces. Okay, and basically you see differences within the noise. But in the post-CHF regime, if you have a dry out at some point or DMB, the chromium coated surface will survive a much longer time. So the coping time will be much longer because chromium essentially work as an oxidation barrier, as a barrier to oxidation. The zircaloy instead will oxidize fairly rapidly, and when it oxidizes, it becomes less conductive. And if it becomes less conductive, the temperature increases even more. So we have kind of a positive feedback that makes the cladding to melt. For chromium coated, what we have observed is that even for after a few seconds or several seconds, the surface is still in good shape. So post CHF is a current target, essentially research target. CHF.
So it's very, I think maybe very big area. How to see that is a temperature range? How about the temperature?
Temperature range can go up to about 300, 400, 500 degrees, depending on where CHF happens. So you start to look into studies that, as of now, are very much applied. Okay, so this experiment in particular that you see here were run with actual rods from Westinghouse and tested with internal heaters. So in relation to this study, these are, let me say, very much applied. That's fundamental. Just want to, get to the bottom of this from an industrial point of view.
Thank you.
Okay, so do you have a question? Yeah. No? Oh, thank you very much, Matteo, and audience for providing a very nice talk and nice discussion.
Thank you.
So
Thank you all. Thank you all.
For this seminar. Thank you very much for the presentation.